All right. So as I said, we're doing a limited number of sections here, sections 3.1 through 3.7. Hold on real quick. Good. And I think someone's unmuted. And again, if you have any questions, please stop me. Please do interact. So this chapter is on matter and energy, but we're only going to talk about the matter portion of it. The energy part will come up later on in the class. So we've already talked about the definitions of this, and that is that matter is something that has mass and takes up space. I use that terminology to define what it is. And matter also can be found in one of four different states: the gas state, the liquid state, and the solid state, and then something called the plasma state, a high energy, usually ionized type of fluid that we will not be dealing with in the class. So we're going to focus on these three states here: gas, liquid, and solid. By a show of electric hands there, how many of you already knew this? Gas, liquid, solid. I would assume most of you. Yeah, good. Yeah, they should have covered that in your previous science classes in middle school, high school. Okay, so now what is matter going to be made up of? Our most basic unit of matter that we really deal with in this class is what is called the atom. Okay, we know that atoms are almost inconceivably small. And as I say here, there's different, what we call varieties of atoms. We can name them differently depending on certain characteristics that they're going to have. When we were first looking at the concept of atoms, it was originally thought that atoms might be the smallest particle that there was. And in fact, the word atom or atomos basically means indivisible, can't be broken down further. In fact, it can be. There are smaller particles in there, things called protons, neutrons, and electrons. And then those can even be thought of as smaller particles, making those up, called quarks. But the atom is going to be our fundamental unit, the one where we'll put most of our focus. Atoms can be held together by what we're going to call covalent bonds. What that's going to mean, as we'll see later in the semester, is that means atoms that are sharing electrons between them. And because they're sharing them, there's a basis of an attraction still holding those atoms together. There's another type of bonding we also talk about later on called ionic bonding. Now, when we talk about molecules, what is a molecule? A molecule is just any combination of two or more atoms. Sometimes it's only two atoms. Sometimes the atoms are the same. Sometimes they're different. Sometimes it can be thousands upon thousands of atoms. Molecules can be huge. But the most important thing to understand about these molecules is that there's going to be a well-defined number of atoms that we can break into a ratio. So for example, water, what's the formula of water?
H2O.
H2O, and that means that there are always in a molecule of water two hydrogens, the H, and one O, the oxygen. That is a ratio that is fixed. It doesn't ever change on us. If it changed, it wouldn't be water. For example, H2O2 exists, and many of you have it in your house. It's called hydrogen peroxide. But you agree, it has different properties than water. You wouldn't go drinking hydrogen peroxide, I'm hoping, okay? You certainly wouldn't get the same effects as you get from water. All right. Now, there are other ways that we can exist the atoms together, and those are going to be called mixtures. We'll be talking about those. But the thing about mixtures versus when we're talking about molecules here, or things called crystal lattices, which we get into as well, is that these other things here will largely be mixtures, meaning they won't have that whole number ratio there. Okay. But we're going to be really focused right now on this idea of molecules where you have whole number ratios of atoms or the same type of atom in a substance. So using graphic art, we usually are going to represent atoms as spheres. That's the easiest way to do it. Atoms aren't really spheres, but this is a good, what we call, model. Okay. We model lots of things in chemistry because what we're trying to do is take a very complicated, abstract idea and make it something that we can wrap our minds around pretty easily, something that we can visualize in our head. And that is one purpose of a model. Okay. So we are modeling atoms here with spheres. Are these nicely organized or are they kind of random all over the place?
Nicely organized.
Yeah, they're nicely organized. If you look carefully, can you see the hexagons here? Like there's a hexagon with one in the middle, and then here's a hexagon with an atom in the middle. There's a very specific reason for that. Okay, that's how they build up. And how many of these atoms are there in this one little tab? I mean, it's a monstrous number, a huge number. So they are that small. The difference over here with molecules is we see many of these spheres touching one another. They're kind of looking like they've merged into one another. This is what we call a space-filling model, where the molecules are just crammed together like that. And you're seeing that there's different colors, which indicates different atoms. So for example, the white are hydrogen atoms, the black are carbon atoms, and the red are oxygen atoms. And each of those are a type of element. Carbon is an element, oxygen is an element, hydrogen is an element. But you'll notice that they all should, although this one is suspect, but they all should have exactly the same ratio of atoms to atoms. Yeah, that one looks weird. That one looks more like, oh, I see the problem. The problem is the label. The label says ethyl alcohol, and this says isopropyl alcohol. Yeah, so they were not careful in the textbook to distinguish between those two. This is isopropyl alcohol, isopropyl alcohol, isopropyl alcohol. But isopropyl alcohol would look just like this anyway. All right, so our states of matter, sometimes called phases. There are three of them again. What are they? They are
Solid.
solid,
Matter, or
Liquid.
gas.
liquid, gas. Good. To distinguish between these, we have two questions that we have to answer that give an answer that's unique to each one of these phases. The first question we ask is, does it take the shape of its container? And then does it completely fill its container? So for example, here I have like Coca-Cola. I'm not making an advertisement for them. But if we look at this here, there's a couple things in here. We have gases and we have liquids. When I say, does it take the shape of its container? In other words, does it adapt its shape to being whatever the shape of the container is? And does it fill container means, does it completely expand to take up all the space in a sealed container? That's what we're going to ask ourselves. So a gas takes the shape of its container. It fills all those nooks and crannies that we have, and it completely fills the container. In other words, they can expand, meaning what? Expanding means to increase their what property? Increase their volume. Good. Something can expand means to increase its volume, or they can be, what's the opposite of expand?
Decrease.
Yeah, but more specific, compressed. Compressed. Okay. So gases expand, meaning increase their volume, or we can compress them, which means to decrease their volume. So yes, they can do both. How is a liquid different? Does a liquid take the shape of its container?
Yes.
Yes. Does it completely expand to fill the container? No. 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 In general, because of gravity, it'll sit at the bottom of its container, unless given some force to push it up. And then so you got a yes and a no. And then solids, the answer would be for both of them. Does it take the shape of its container? No. Does it completely fill its container? No. Okay. You might say, well, what if I took a very finely divided solid like sand? if you have very, very small particles, it might look like it's taking the shape of its container. But if you were to blow it up at a microscopic level, you would see where it's not completely able to take the shape of its container. So just think of a regular rock. If I try to take a rock, or let's just say here, container, pencil. Is the pencil going to suddenly change its shape to adjust to the container? No, solids don't do that. All right. So looking at our matter here, we've got 3 examples of water. We have solid water, and of course that gets a name. We call that ice. We have liquid water, for which we don't really have a special name. Usually when someone says water, they typically mean liquid water, but we'll be specific. So liquid water. And then gaseous water, which of course would be called steam, right? Which of these is the most organized? In other words, do you see a pattern, a clear pattern with?
Liquid?
Not the liquids, no.
Solid.
The solids, yeah. If you look, it's the repeating pattern over and over and over, layers on top of layers. You see the same pattern receding back and back and back, okay? And when we think of ice in particular, it can form very, very specific patterns. You can't really see it all that well with this picture, but there are hexagons within the structure of this. That's important because if we extrapolate that to an even greater level, and look at snowflakes, what we see is that we get some really gorgeous patterns that can repeat themselves over and over and over. So like, for example, here is a snowflake, although this one actually looks more fake than real. Let me look at the Caltech. Caltech has a great page of snowflakes. Where they actually visualize and photographed several different examples. For example, here is one, and you can clearly see that the hexagon is an important structural element of this hexagon, of this snowflake, right? 6 sides, 6 sides. So the importance here, and this is how we really want to learn chemistry, is we're taking something at the very smallest levels, like water molecules that are in a very organized pattern here, and seeing how this pattern continues to exert itself on an even larger scale. And that's really going to be, I think, the basis of a lot of your success in chemistry is, can you see what's at the very smallest level and visualize how that impacts matter at a, what we call a macroscopic level, a level that we can see. Liquid particles aren't organized like solid particles, but what do they have in common compared to gas? Notice that the particles are pretty close together, right? They're not really in a regular pattern. And we know, of course, if you take liquids and shake them, they're going to move around in their positions. Gas particles, you'll notice, are very different in that they have large distances between them. And these distances in this diagram are not really shown nearly to scale. They should be much further apart than they are here. But this is just to emphasize again, there's lots of empty space in gas particles, between gas particles. Okay, so with solids and liquids, as we said, the particles are close. In gases, they're far apart. And we talked about whether or not something takes its shape or its volume, and also whether or not we could compress the matter into a different shape. We did not talk about the motion of the particles, and so I want to be kind of clear about that. Clearly, with a solid, again, pencil here, the particles are not moving too much relative to each other. But at any temperature other than absolute zero, the particles are always in some kind of motion. What's going on here in this solid liquid, in solid ice, is that these particles are vibrating in place. They're just oscillating. Okay. As you increase the temperature, they will oscillate more and more until eventually they can break free of one another and be like a liquid. There's a lot more motion here with particles relative to each other. Now, they still need to stay next to each other, which means that they're going to kind of roll over one another, but they still have to somewhat touch or keep a very small distance between them. So there's quite a bit more motion here, but it's limited to within the volume of the liquid. A gas, on the other hand, is free to move throughout all of space, in theory. Okay, so you have a lot of motion associated with gases, the least motion associated with solids. Okay, so do be aware of that. Even though you're not suddenly turning into a liquid, puddle or anything, you are a solid for the most part, at least on the outside, we're solid. The particles inside of you are always vibrating. They're always in some kind of motion. All right, any questions on any of this stuff up to this point? Anything? Okay. Now, staying with solids a little bit longer. If we look at solids, not at the level that we're used to seeing them, so to speak, what we call a macroscopic view, but at a submicroscopic view, below what even a microscope can do, a regular visible microscope, we'd see that we have a couple different types of solids. We have crystalline solids. Crystalline means that there is a regular pattern that exists within the matter. Okay, so a pattern that repeats itself over and over and over throughout generally 3 dimensions. Ice, we saw just a second ago, was a crystalline solid. It has its particles arranged in a very specific way. Salt, we would see that the atoms that make up the salt are arranged in cubic kinds of structures. Diamonds, they're arranged in a form that really wouldn't make sense for me to talk about right now. It's what we'd call chair forms, but we won't worry about that for right now. But it's a pattern that repeats itself over and over and over. On the other hand, we have some solids that are, let's say, a little bit more slippery. They're not quite as rigid in their structures. Like, for example, your own skin, right? Your skin is not a rigid solid. You can kind of bend it around. There are real issues there. And so there's usually less organization within those solids. And in fact, if we look carefully, the positions of the atoms might seem to be random. There's usually some kind of underlying structure, but that structure isn't repeating units like we get with a crystalline form. I think probably the best one to look at would be rubber, because we all know you can take rubber and you can easily stretch it out, right? It's totally the opposite of something like a snowflake or ice. You can't stretch ice with your hands because of the rigid structure that's there. Glass might surprise you because you might think of glass as rigid. It is in fact rigid, but the atoms that make it up are not in very nicely organized patterns for the most part. Plastics, styrofoam, all of these kind of are basically liquids that freeze into a certain position. And so they just take the position that they were at when they froze into them. Whereas crystalline solids tend to very slowly freeze into specific patterns. So if we look at silicon dioxide, for example, I'm sure you've heard of quartz. Quartz, if we look at it, has this kind of nice arrangement of atoms where we see one silicon atom in between 3 in a kind of a pyramid type of an organization. You can't see this really in 3 dimensions. And then another pattern of those, and then another pattern. And so you'll notice that this pattern goes on and on and on. We could keep this pattern going off all over, and we'd see this nice pattern throughout. But let's say we took silicon dioxide here and we heat it up until it's a liquid, and then without paying too much attention to what happens, we let it re-solidify. What we start getting is the patterns start to break down. So we might see a pattern here, and we can see the elements of a pattern in here, but they've mostly broken down throughout. And that's what we see with an amorphous solid like glass. Now, obviously, when you look at glass, you can't see the individual atoms, but we know that the structure is something like this. Incidentally, glass almost has a kind of a liquid quality to it. If you take a pane of glass and just leave it there for years and years and years, over time, if you look at the bottom of the glass pane, it'll seem to get thicker towards the bottom. We've seen this in Europe with some of the really old glass that was created for cathedrals, where it's literally seems like it's dripped internally down to a lower form. So you actually get that over many, many years with these amorphous solids, whereas you're not going to see that with a crystalline solid typically. All right, so we've talked about our states of matter, and which state a substance is in depends on two things: the temperature, and then later on we'll get into the pressure. In Chem 130, let me get my notes up here. You don't need to know this right now, but in Chem 130, what you will get at some point is we'll see that we can actually graph these things here in what's called a phase diagram. So for example, a phase diagram for water will look something like this. So let me see, what do we have on this axis? I always forget, but I believe it's pressure on this one and temperature on this one. I might need to change that in just a second. Yeah, I've got those backwards. And what this tells me is, if I go ahead and I look at this diagram, I would find that at very high temperatures, what do you tend to get? Gases, liquids, or solids?
Yeah.
Yeah, just think about water for an example. And then at the lowest temperatures, you get solids, and then you get liquids right here. Good. So the idea here is, if you know the temperature and you know the pressure, you can find the state of matter using one of these diagrams. So for example, what we find with us is, if we're dealing with a pressure of room pressure, like 1 atmosphere, we can go ahead and draw a straight line here. So say this is water. So this would mean that what? At what temperature would water be a solid?
Low temperature.
Yeah, so it'd be like at 0 degrees or below, it's a solid. And then what would this have to be right here? This would be 100 Celsius, right? At 100 Celsius, water would turn from a liquid into a
Gas.
Yeah. So that's what these kinds of diagrams allow you to do, figure out what state this is in. And in fact, if we wanted to really make this complicated, we find that with water, there's actually many different types of ice. So this can be actually even subdivided into different forms depending on the pressure and the temperature, although it's not apparent from just looking at it. All right, in terms of the states of matter, I don't know why, but I didn't really, well, I don't need this. So I'll just go straight to the different states of matter. All right, we have different terms that we associate with each different type of a change. So for example, when something changes from a solid to a liquid, what is that called? You should know that terminology. Just think of ice. Ice does this. It melts, yeah. Good. And what do we say is happening when it goes from a liquid to a solid?
Freezes.
Freezing. Good. Let me get that all the way. Liquid to a gas there's a lot of terms that go with liquid to gas. Can you give me one term of what happens when a liquid goes to a gas?
Boiling.
Boiling. Good.
Would melting be another one?
No, a gas doesn't. A liquid doesn't melt.
Evaporates.
And this happens, by the way, at the boiling temperature. So this has to be at a certain temperature. We call that the boiling point. Okay. What else? When can water change to a gas, but it's not at a high temperature? What would we call that? You see it on the ground all the time. Spilled water would
evaporate.
Evaporation. Good. This is below the boiling point. Right? Because water doesn't have to be at 100 Celsius to evaporate. Or we could use a generic term for all of these. And so usually I'll use this term, which is just vaporization. Technically, where in the liquid is evaporation occurring? I'm not sure that anyone would know, but it's not throughout the whole liquid, but only at what part of the liquid?
The surface.
The surface. Yeah. In evaporation, what happens is the particles at the surface get kicked with a burst of energy by the nearby particles. And if they get kicked with enough energy, they can go from the liquid to the gas state, and they'll usually take off. And if they're not in a container, they're probably not going to come back. Okay. And that's what we're seeing there. So how fast it evaporates depends on how much energy the particle has, which depends on temperature. High temperatures, liquids tend to evaporate quickly. The big difference between boiling and evaporation is in boiling, you observe coherent bubbles. Like think of water when you're boiling water, there are bubbles of steam, right? Okay. And they rise to the surface and escape. In evaporation, you don't see that. The reason is below the boiling point, any bubble that starts to form in the liquid will collapse because of the atmospheric pressure. It will crush it, too high of a pressure. So it's not until you get all the way to the boiling point that there is enough internal cohesion in a bubble that it can rise and escape. All right. That's something we'll worry about later. So bubbles with boiling, no bubbles with evaporation. Incidentally, when you first go to boil water, you notice that there are little bubbles that start to form pretty soon, right? Those aren't steam bubbles. Anyone know what those bubbles contain? When you first go to heat water, they're not steam, primarily.
Is it the oxygen?
And
Carbon dioxide?
yeah, anything in the air. Yeah. What happens is gases from the air will dissolve in water. So not very much nitrogen, but definitely oxygen and some carbon dioxide. They're definitely there. If you were to boil water and then take that boiling water and put it in ice cube trays and then freeze it, you'll see that the ice freezes solid. Excuse me, not solid. It freezes transparent. You know how ice cubes normally are opaque? You can't see them through them. That's because of the air trapped within the ice structure. If you boil off all the air and then quickly freeze it, very little air will be able to redissolve in the ice, and you'll see see-through cubes. Okay, so that's boiled water that you would need to do that. But yeah, it's definitely there. And what evidence do we have that there has to be oxygen in the water? From life, we know that fish also need O2. They need the same. They breathe the same thing that we do. O2, not the H2O, not the O in H2O, but O2. They need that that specific formulation in order to live. Okay, gas to a liquid. Anyone know the name of that term? That's called
Condensation.
good. Try to do this sideways. Condensation. Or condensing would be probably the right way of saying it. Most people aren't as familiar with the other changes here. Solid to gas. Anyone know what that's called? If a solid doesn't become a liquid, but immediately goes to a gas, that's called
Sublimation.
sublimation or subliming. I'm not even going to try to write that sideways. The process is called sublimation, but we could call it again subliming. Can you name me a compound that or a substance that does that you're aware of?
Nitrogen.
Nitrogen generally does not. And well, to my knowledge, I've never seen solid nitrogen. Liquid nitrogen very quickly boils, evaporates off or boils.
Would it be water? Or like
Sometimes.
or vapor or something?
Sometimes water can sublimes. You'll notice that
What
because your ice cubes gradually get smaller and smaller and smaller if you leave them for over time, right? So that's some of it. But the most important one that you're going to see on a not daily basis, but a more often common basis would be dry ice. And dry ice is what? Anyone know what compound dry ice is?
Is it carbon dioxide?
Carbon dioxide. Yeah. So carbon dioxide at atmospheric temperature, it goes straight from the solid phase to the gas phase. In other words, if I was to draw a line, it would be like this. As it gets hotter, it doesn't go from solid through liquid to gas. It goes straight from solid into gas. That's subliming. And then the least common is gas going to solid. That's called deposition. Like the word deposit. Good. Now we can break matter down into a few ways of classifications. First, we're going to look at what are called the pure substances and the mixtures. So that's our first major divide. Pure substances versus mixtures. And then within each of those categories will be two other categories. So pure substances are the elements in the compounds. The mixtures are the homogeneous mixtures and the heterogeneous mixtures for ultimately 4 levels that we're going to be dealing with here. So when we talk about pure substances, the phrase that's important to keep in mind is that they have a consistent and uniform composition. Okay, so uniform means, regular. It's the same over and over and over. It doesn't, something that's not changing with this. And so those are our elements and our compounds. When we're talking about elements, they are made up of the same type of atom. So you won't see any other type of atom, any other type of atom in there. So nitrogen is one, neon is one, copper is one. Whereas compounds contain atoms in a whole fixed numbered ratio. I need to change the definition of that. That's not correct. Of at least two different types of atoms. Oxygen, for example, can be found monatomic by itself, which is very, very unusual. It's usually found as O2, though. Okay. It's sometimes found as O3. Anyone know the name of what that is called?
Ozone?
Called ozone. Good. So these are elements. On the other hand, carbon dioxide is a compound. It contains two or more different elements in a whole number ratio. So two or more different elements, different types of atoms, in a fixed whole number ratio. And that ratio is atom to atom. It cannot change for that compound. The number of elements at this point are limited. I think it's theoretically possible to have an infinite number of elements. That's certainly not practically likely to happen. In fact, I don't know the theories whether you can actually get an infinite number of different types of atoms. But at this point, we only know of 100 and I believe 18. And some of those had to be man-made. And those are enumerated in the periodic table of the elements. Okay, so these are two types of pure substances. On this type, we have only aluminum atoms. So this is an element, right? Aluminum is an element. Here we again have our alcohol. And this contains multiple different elements in a whole number ratio. So this is a what?
One.
A element or compound?
Compound.
Compound. Good. Compound. Good. Here's a helium balloon. And if we look inside the balloon, and only inside, forget the rubber part of it, you see only helium atoms. So helium is an element. Good. And this is sodium chloride. This is just table salt right here. Now, this is not a molecule here, right? Not a molecule. This is what we'd call a crystal lattice. But you'll notice if you look carefully that the ratio of the greens, which are the chlorides, to the sodiums, which are the purple, is 1:1. For every one green, there's always one purple. So this is a compound because it's got that fixed whole number ratio, 1:1. By the way, this is just like the corner of one side. This would go on almost infinitely. It would seem infinite if you were like stuck inside of it. It would just seem to go on and on and on forever. There's, billions of those patterns repeating themselves over and over. Okay, so the key word again, or phrase is, fixed whole number ratio. Now, with mixtures, we do not get a fixed whole number ratio. So we might be able to get an artificial ratio, but it's always going to have some uncertainty in it. So for example, let's look at salt water. Salt water has H2O and NaCl in it. H2O is water, NaCl is just plain old table salt. So H2O is a what? By itself, it's what kind of matter? Element, compound, or mixture. By itself, it's just a
Compound.
good. And NaCl by itself? One sodium for every one chlorine is
Mixture.
Compound.
also a compound. But now I put them together and we have a mixture. Because even no matter how careful we are when we mix these, is it really possible to get the ratio down to atom by atom? Turns out
No.
you can't really do that. No. So yes, you can make a mixture that's 100 grams of water for every 100 grams of sodium chloride, and you can get a pretty good idea of what the ratios are between the atoms there. You can certainly do that, but there's always some uncertainty in there because you have to measure it. So in other words, these numbers are what kind of numbers in a formula? They are exact. H2O is 2 hydrogens exactly for every 1 oxygen. NaCl is exactly 1 sodium for exactly 1 chlorine. Whereas with mixtures, there's always some uncertainty, which comes about when you make the mixture. Okay, homogeneous mixtures are when you have all parts in the same state. So all things are gas, all things are liquid, or all parts are solid. And furthermore, all the parts must be evenly mixed throughout. And we're going to say that from a visual standpoint. It should look visually the same on this part, and 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 this part, etc. Okay? It should look visually consistent throughout. And a heterogeneous mixture is a mixture which does not meet the requirements of homogeneous. Okay. Okay, so on the left, I have, for example, salt water. If you look here, and you look here, and you look here, and you look here, it all looks the same throughout, correct? So it is a homogeneous mixture, assuming that this thing at the bottom is just the light. Okay, there's no solid down there. We're going to assume that's just light. Mud, on the other hand, is what kind of a mixture? Homogeneous or heterogeneous? Heterogeneous, yeah. And we can clearly see that because number one, you've got liquid and solid. And even if you only looked at the liquid, you see it's not consistent throughout, is it? It's much lighter up here and much darker down here. So that would be kind of the hallmarks of a heterogeneous mixture here. It needs to look consistently the same throughout. Now, there are more complicated things here than simple homogeneous, heterogeneous mixtures. Colloids, for example, are types of substances which fall into a gray area. So there's a bunch of gray areas we're not going to get into. Like, for example, milk. Milk is a little confusing. Marshmallows would be confusing because on the one hand, they look visually one way, but if you put it under a microscope, you'll see that a marshmallow has lots and lots of little holes in it, okay, because of air that's trapped within it. So it kind of changes depending on your visualization level. All right, so let's take a look at each of these and decide whether they're homogeneous, heterogeneous, as far as mixtures. So these are all mixtures. Okay. Vodka, which looks like it's water mixed with ethyl alcohol. First of all, what does it look like? Someone asked you, what does vodka look like? What would you say it looks more like than anything else?
Just water.
Just looks like water, right? Obviously, it's not water, but it's water and ethyl alcohol mixed together. So It looks just like water. So homogeneous or heterogeneous?
Homogeneous.
Yeah, it's homogeneous because it looks pretty much consistently the same throughout. I'm not going to write why because I just said why. For the heterogeneous ones, I'll offer an explanation. Cheerios in milk. Homogeneous or heterogeneous? That should be a really easy one. Come on, guys, participate, please.
Heterogeneous.
Heterogeneous, very good. And what's the main reason why it's heterogeneous? Because you have
Solids and liquids.
very good. We're not even going to get into the milk. Good. About oil and water?
Heterogeneous.
Good. Also heterogeneous. And why is it heterogeneous? It's different from the, not for the same reason as cherries and milk, but it's because it has
Oil.
Color as well. So the oil.
is, but why? The definition is because even though you have two liquids, they are,
Non-soluble.
yeah, they're, the word it would be immiscible, but we'll just say which do not mix. They're not soluble in each other. So whenever you get same state, but they don't mix evenly, and you get that with solids and you get that with liquids, it would be heterogeneous. Salt water, we already said was homogeneous, right? Unless there's any solid at the bottom, and then it would be heterogeneous. But generally, we'll just assume everything's there. How about just plain old air, like the air that's around you right now? Homogeneous, because again, what's in the air? What's the main
combination?
air?
Oxygen and nitrogen.
Nitrogen, yeah. Air is mostly nitrogen. And then number two would be what you need to live.
Oxygen.
Oxygen.
Good. And then number three, you might not know, would be like argon. And then on a particularly humid day, you also have quite a bit of water, and you also have carbon dioxide. So you have many different things mixed together. And is air exactly the same here as it is higher in the atmosphere versus over the ocean, or does it change?
It changes.
Yeah, it's not a fixed ratio. At least in any particular, if you could take a chunk of air from different points on the Earth. And then finally, dust-filled air would be considered
Heterogeneous.
Good, because
There's two solids.
yeah, there's solids mixed with gases, two phases. How far? Oh yeah, good. I'm almost done with chapter 3, which means I can probably answer some questions. on chapter 2. Okay, we can separate the different components of a mixture by physical methods, and kind of explaining that can be a little bit tricky here. But basically that means, by heating them some way or physically putting them through a filter or things like that. In other words, without doing a chemical reaction, So a heterogeneous mixture of coffee grounds and water. We can separate coffee grounds and water by using a filter, right? And if you make coffee using a coffee machine, that's how you do it. You separate these with a filter. Water can be removed from salt water solution, which is a homogeneous mixture, by boiling the water off. So you're just supplying heat. You're not doing a chemical reaction per se to the salt water. You're just making the water leave. You're giving it enough energy that it escapes from the salt, so the salt stays. So there's no chemical reaction involved there. But compounds, the only way you can separate them into their individual elements is you need a chemical reaction of some type. And that can also be done using an electric current in some cases. So we'll say a chemical reaction and or electricity, which will initiate a chemical reaction. Okay, so here we have two elements. Here I have iron in the form of iron fillings. Anyone know what that yellow powder is? It's another element.
Starch.
That's a compound.
Yeah.
I'm not sure if anyone would know. That is sulfur. Okay. So we have iron and we have sulfur right there. Let's say I put them in different test tubes and I test them with a magnet. You'll notice that the iron fillings are definitely affected by the magnet. They're attracted on the different poles, and in fact, they're kind of forming this kind of interesting snake from one side to the other. The sulfur could care less about the magnetic field. It's not in any way affected by the magnetic field. Now, what we have right here is a mixture of iron and sulfur. So all someone did right here is they said, let's take the iron and the sulfur, stir them up together, and put them in a test tube. It's a heterogeneous mixture, I think you can see, right? Because it's not clear and visually throughout here. The iron is still attracted to the magnet. So we have a mixture. But if you heat this up and give it enough energy, iron and sulfur react to form iron sulfide. Actually, the name would be a little more specific, but we'll worry about that later. So this is after heating them, and we've done a reaction. Now it's no longer iron and sulfur. It's iron sulfide. It's a compound with totally different properties, usually distinct. So if I try the magnet here on iron sulfide, you'll notice nothing happens at all. The iron seems to have lost its distinctive magnetic property as a result. There are many cases when these kinds of things are, when compounds are very different from their elements. Like, for example, water. Hydrogen is very flammable, will easily catch fire. Oxygen will burn with most elements. But water, does it catch fire?
No.
No. The hydrogen in water is not, it's no longer supposed to be thought of as being, hydrogen anymore. It's a compound, water. It's distinct and it has its own properties. Okay, other ways of separating. So we talked about separating here. This is called a filtration. In a filtration, you just use filter paper to catch solids, but allow liquids to go through. And this is pretty much exactly what you have in a coffee maker, correct? You have a solid piece of filter paper, a liquid with solid and liquid. The solid gets retained by the filter paper, the liquid goes through. Something we spend a lot of time on in organic chemistry is this thing right here, which is called distillation. Distillation is when you want to separate a mixture of liquids. Let's say there's two liquids here. If there's two liquids, the one with the lower boiling point will tend to boil off quicker than the one with the higher boiling point. And when it reaches high enough, the glass gets cooler and cooler as the gas goes higher. And it eventually comes into contact with this piece of glassware, which is cold. We have cold water going into it and cold water going out. By the way, that's going around a tube here. So it's a jacket going around a tube. And so this inner tube is very, very cool. So the gas condenses, right? Goes from gas to liquid, and then gravity pulls it down. So that's what distilling is. Separating using physical properties. So you didn't change the molecule, you just changed it from a liquid to a gas. It's still the same substance. All right, so in summary then, matter can be broken into pure substances and mixtures. Elements contain only one type of element. Compounds contain two or more elements in a fixed whole number ratio. Mixtures can be homogeneous or heterogeneous. Homogeneous means that they are visually consistent throughout. All liquids are mixed with other liquids. Any solids would be mixed with the liquid or what have you. You don't see two different phases. A heterogeneous mixture like marble here, this is a solid version of one, you can see visual differences between them. They're not perfectly mixed consistently, so it's heterogeneous. Okay, so let's classify these things as elements, compounds, homogeneous mixtures, or heterogeneous mixtures. Notice there's not going to be any homogeneous compounds or heterogeneous compounds. I will only use the word homogeneous and heterogeneous in front of the word mixture. So that's 4 different substances there, or 4 different classifications. So tap water. What would probably best describe tap water?
Homogeneous.
What's that?
Homogeneous.
Yeah. Well, in Whittier, some places it's actually heterogeneous, but homogeneous because it looks like just plain old water, right? You can't tell it apart from other water. But is there anything inside the water? There is, right? There is fluoride ions for our teeth, sodium ions. There's probably some carbon dioxide gas trapped in it. There's calcium ions. There's all kinds of different things in it. Okay, so that would be a mixture. It's not a fixed 1-to-1 or 1-to-2 kind of a ratio. So tap water is a homogeneous mixture, usually, unless it had solids in it, in which case it'd be heterogeneous. So let's just assume homogeneous. Steel. Steel is an alloy. You make alloys by taking metals, like pure element metals, melting them into a liquid, and then mixing them and letting them, and then stirring them in special techniques to mix them. And alloys can be mixed in all kinds of different proportions. For example, there's many types of steel, many different grades of steel, depending on what's mixed in. So based on that, what would be the best way to describe steel? Assuming it looks the same all throughout, what would you call it?
Could also be homogeneous.
I would call that a homogeneous mixture. Yeah. So long as it looks the same throughout. So if I had a steel rod and it looks the same all the way through, it would be a homogeneous mixture. Good. What are a couple other alloys? Can you name me 2 other alloys? Combinations of metals.
Gold and copper, maybe?
Gold and copper are elements. If we look on the periodic table, and that you just have to have experience. But if you look on the periodic table, gold and copper are elements. And in fact, going back to, remember I put up the flashcard set to That's under the handouts also. These are all elements, okay? So anything appearing here would not be an alloy. So for example, copper is an element and gold is an element. So like
Did
platinum.
someone already mention bronze is an alloy?
Bronze is an alloy. Good. Bronze is one. Very good. Any others?
Nickel.
Nickel's an element. Although the nickel in nickels is probably an alloy. Okay, there's probably something else in it. Bronze, another one that begins with Br. Very shiny, looks gold. Brass, very good. Thank you, Isaiah. Brass is another alloy. So your most common alloys are things like brass, bronze. Brass, I believe, is copper and tin. Bronze is copper and zinc. Sometimes I mix those two up. Okay. And then other
Would
things.
anything plated be considered an alloy?
That's a good question. And I don't know that I want to give a formal answer on that. I think you could answer it in different ways, because on the one hand, it's one thing on the top and one thing on the inside. It would look like a homogeneous as you look at it. But to be a true alloy, it should be mixed completely throughout. So I wouldn't call that an alloy per se if it's not all mixed.
Stainless steel an alloy?
Yeah, what's that?
Stainless steel, right?
Yeah,
Okay, no.
all the different kinds of steels are alloys. The main element is what in steel? Anyone know? Or should be. The main element is iron, I believe. Okay. Other alloys would be like anything karat gold. So if it's not pure gold, 24 karat gold or whatever, there's different kinds of gold that are mixed to various degrees. Good. So alloys are generally homogeneous mixtures, generally. Helium. We already saw helium. It is an element. Mud, we already saw. It's a heterogeneous mixture. Very good. And carbon dioxide, which has one carbon atom with two oxygen atoms, always in that ratio, would be a compound. Very good. Okay, now we can describe matter in two ways: chemical properties and physical properties. I'm going to start off with chemical properties. And a chemical property just tells you how matter interacts with other types of matter. And so it's always going to be something about how it reacts in some way. So for example, hydrogen reacts with oxygen to make water. That's a chemical property. It's something that hydrogen has the capacity to do. Saying how something doesn't react is also a chemical property. So helium doesn't react with anything is a chemical property. Burning means reacting with oxygen. So whenever someone talks about something is flammable, that is what kind of a property then? Chemical or physical? Flammability refers to a chemical property. It means reacts with oxygen under special conditions. Physical properties are all the properties that do not have to do with how something reacts. So for example, the state, whether it's a gas, liquid, or solid, the freezing point, the boiling point, the density, the color, the clarity, whether something is clear or opaque. All of those have nothing to do with reactions. They're just different ways of describing it without saying how matter interacts. Now, I'm not sure why we make this distinction, but we also do the same thing for changes of matter. Now, to be clear, a property is the ability to do something. The change is actually doing it. Other than that, they are the same idea, right? So a chemical property is I have the capacity to do this reaction. A chemical change is I am actually doing this reaction. Other than that, there's no distinction. So don't worry about the difference between a property and a change. The difference that you need to worry about is chemical versus physical. That's all that really matters, chemical versus physical. So a chemical change involves a reaction, which means atoms somehow get rearranged in some way, and you get some chemical substance that wasn't there before. So rusting, for example, you have iron atoms, and then water gets on the iron, oxygen dissolves in the water, and at where they meet, iron will react with the oxygen. So you had iron before, you had O2, oxygen before, at the end you have Fe2O3. You have a new chemical substance that wasn't there before. It's a chemical change. A physical change doesn't involve a chemical change. So for example, a boiling water, you're changing liquid H2O to gaseous H2O, but it's still H2O. No new formula, no new substance. Breaking glass. You had glass before, you have glass after, right? It's still the same substance. Something evaporating. So all changes of state, all of these are physical changes. Okay? They don't change the substance, just the location of the various molecules. The last thing I'm going to talk about right now is this most, probably to me, the single most important thing. Oh, and let me show a picture and then we'll do it. So a butane lighter here. If you open the lighter without sparking it, what happens to the butane? It goes from being liquid to a gas, but it's still butane, right? The particles are all close to each other. In liquid butane, they're farther apart as gaseous butane, but it's the same molecules. On the other hand, when you spark it, the butane is reacting with what in the air? That's you're not seeing here. What's in the air that butane needs to react with?
Oxygen.
Oxygen, yeah, O2. So butane plus oxygen gives you carbon dioxide and water. Okay. The water is in the form of steam. You obviously don't see liquid water flying out of one of these things. So it's coming off as steam. So carbon dioxide and water. And it's also producing light and heat in the process. All right, so for me, if there's nothing else that you remember from this class 20 years from now, the thing I really want you to remember that makes the biggest impact of everything in this class, and granted, I don't examine people a lot on this, but it's just a fundamentally important thing to know, is what's called the law of conservation of mass, which in words essentially says this: matter cannot be created or destroyed in any chemical process. And furthermore, in any chemical process, any chemical reaction, it is not possible to change one atom to another type of atom. Hydrogen cannot become oxygen, oxygen cannot become gold, gold cannot become uranium, or anything like that. Okay? So that means for any chemical process that you're dealing with whatsoever, in other words, from combining chemicals and just heating them, any process of that type, you never change the atoms, just the way they are arranged. So a chemical reaction rearranges atoms, but doesn't change them. So if you start a process with 10 million hydrogen atoms and 10 million oxygen atoms, you will always end the process with 10 million hydrogen and 10 million oxygens. You might say, well, wait, but you produce water. Yeah, I do. But it's still the same number of atoms. You can't create them out of nothing. and you cannot destroy them. If you're heating charcoal on a barbecue, let's say you have 2 pounds of charcoal at the beginning of the day. After the barbecue, you look at the ash, and let's say you only have 0.1 pound of ash. Have you violated the law of conservation of mass? Is it possible for you to violate the law of conservation of mass?
No.
No. You can't violate the law of conservation of mass by doing a barbecue. Where did all the rest of the mass go?
In the air?
Good. Good. As what? As I mentioned here, when you burn something, it becomes primarily carbon dioxide and water. Yeah. So all you did was you did a chemical change, but the solids became other chemicals that were gases. Are they probably going to ever come back and reform the charcoal? No. Once they're gone, they're gone. But they aren't destroyed. If you were to put this all in some kind of a sealed container, you would see that the total number of atoms of each type is constant. It doesn't change within that box. It can't. Now, what became very shocking then was about 100 years ago, we started to see something that violated this very sacred law of conservation of mass. So the way I used to phrase it, or we would have phrased it, was matter can be neither created or destroyed in any process. You'll notice I add this word chemical. That clarifies it. So that's any kind of an interaction where you just mix things together and heat them, or they come into contact. What other kinds of processes that we don't talk about in this class do lead to changes of atoms from one type to another? Does anyone know? It's a different kind of a reaction, something called a nuclear reaction. Okay. Nuclear reactions are different entirely. We'll spend some time probably, well, if you have me for Chem 140, I talk about it. I don't think anyone else does. But in physics, you will talk about that. Chemical reactions are all going to be about one very important particle called the electron. It's all about moving electrons around. That will never lead to a change in the type of atoms. Nuclear reactions are an entirely different kind of thing. They're different in very vast different ways, and they give off vastly greater amounts of energy. So we will not consider nuclear reactions. You're not going to be carrying out any nuclear reactions at home for this class, okay? Just not going to happen. Build your own nuclear reactor doesn't sound like a good idea. Incidentally, you are carrying out a nuclear reaction right now. Your body contains carbon dioxide, which contains a little bit of carbon-14, and that little bit of carbon-14 is radioactive, so you're always seeing some changes, but at a level that you really can't detect at this point, probably. All right, so that was chapter 3. Chapter 3, as you can see, went much faster than chapter 2. It's mostly a concepts chapter, and I would argue it's the easiest chapter.